Howdy, and welcome to a Mean 315 enhancement lecture, where today we'll talk about an example problem where we look at a steady-state device that the substance flowing through that steady-state device is undergoing what we call a polytropic process. We'll talk about what that means, polytropic process, as we go through the example problem. And we'll also, as I work through the example problem, I'll also follow a typical solution methodology that works for me and might be something that is useful for you as well as you work through homework problems and other types of problems, thermodynamic problems. Okay, so what we have here is we have steam that enters a turbine, and the turbine is operating steady state with a pressure of 6,000 kPa, a temperature of 450 degrees C, a mass flow rate of 15 kilograms per second. Those are the inlet conditions for the steam. And the steam leaves the turbine through an exit flow area of 0.22 square meters. We're told that if the steam expands according to the relationship PV to the 1.2 equals a constant, that's the polytropic expression, and I'll talk about that a little bit more. We're asked to determine the exit temperature and the exit pipe velocity if the exit pressure is 100 kPa. Okay, so let's work through this example by, the general methodology that I follow is I'll first draw a diagram so that I can visualize everything that I'm working on, and then I identify the state information that I know. In other words, the properties that I know at state I and state E, the inlet and exit states. I write some information about the process, and then I also help remind myself what it is that I need to find by writing down what I want to find, basically. Okay, so let's first of all start with our diagram. So we have, of course, our turbine, and so we just generally draw our turbine like this. And of course, a turbine is meant to produce power, and it does so by having an inlet flow. So this will be our inlet state. And then we have our exit state. And then I'll also, just for completeness for our general control system, I'll draw this Q dot on here. As we do more and more of these steady state device problems, that Q dot won't be there. We'll be studying what we call adiabatic processes, which means that there's no heat transfer. But just for completeness, I'm going to go ahead and write that there for now. Okay, so that's our diagram, and we can go ahead and draw or identify the state information that we know. So we'll first start with the inlet state, which I'm calling state I. And in the problem statement, of course, we're told that the inlet pressure is 6,000 kPa, so we can write that down. We're told that the inlet temperature is 450 degrees Celsius. We're told that the inlet flow rate, or m dot I, is equal to 15 kilograms per second. There we go. We then have the information that we know at our exit state, so we can write down our state E information. So what we know at state E is we know the exit flow area, so we know A sub E, and that's 0.22 square meters. And we know that the exit pressure, PE, is 100 kPa. That was also given to us in the problem statement. Okay, so what kind of process are we studying here? Our process, there's two pieces of information that we know about the process. First, we know that it's a steady state process. Our turbine is steady state. So the turbine, the water flowing through the turbine, or the turbine itself, I should say, doesn't undergo any changes in mass, energy, or entropy. And then the second piece of information that we know is that it follows this polytropic behavior. The steam, as it flows through the turbine, follows this polytropic relationship, which is that the pressure times the volume raised to the exponent 1.2 is equal to a constant. And then finally, the last piece of information that I like to write down is just something to help me remember what it is that I want to find. And there's two pieces of information. One, I want to find the exit temperature. And two, I want to find the exit velocity, v sub e. Okay, so now in writing out the solution, what I typically like to do is I like to think through the problem first and try and understand how I can work it such that I get to the exit temperature and the exit velocity. So a good starting point will be our generalized equations, things like conservation of mass, conservation of energy, and the entropy equation. Now, we're not quite far enough along yet to know how to use conservation of energy or the entropy equation for this type of problem, the turbine problem. We need to first learn a little bit more about work processes, but we can certainly use the conservation of mass equation. And so if we just go ahead and start to write out our solution, then basically what we can say is that since the turbine is steady state, where this is important, this piece of information, what that means is that our conservation of energy equation, conservation of mass equation is the following. The sum of our inlet flow is equal to the sum of our exit flow. Since there's only one flow in and one flow out, there's only an inlet flow and one inlet flow and one exit flow. Our conservation of mass equation simply becomes m dot I, there's no summation, is equal to m dot E. Mass flow in equals mass flow out. Okay, so that'll be useful later on because we know that our inlet flow, for example, is 15 kilograms per second, and so that necessarily is also what our exit mass flow rate is. Okay, so let's think about this polytropic process now. And so basically, whenever we call something a polytropic process, right, a polytropic process is one having the form of PV to the N is equal to a constant. So pressure times specific volume raised to the constant. And this N is called the polytropic index. Okay. So in the case of our problem statement, where we have PV to the 1.2 equals a constant, N is equal to 1.2. Okay, so for us, N equals 1.2. Okay, so how do we use this? Well, since PV to the N is equal to a constant, what that means is that my inlet pressure times my inlet specific volume raised to the N, that's equal to a constant. And so since my steam everywhere through my turbine follows this relationship, that means that my exit pressure times my exit specific volume raised to the n is equal to that same constant. And so I then have a relationship now between my inlet state, Pi Vi to the n, is equal to Pe Ve to the n. I now have that relationship. Okay, well, let's think about this and see what we know and what we have to find out. Well, first of all, Pi is known. This is given to us. Okay, so that's a known property. Okay, and Vi is known. And the way that Vi is known is Ti and Pi are known. So I can go to my table and find Ti and Pi and thereby determine Vi. Pe is known. That is also given. So I can use my polytropic index, or my polytropic equation to solve for my exit specific volume. Then that will give us two independent properties at the exit state. And those two independent properties at the exit state, at state E, are the exit pressure that was given and the now calculated exit specific volume. So state E is fixed. We know two independent properties at state E. We can solve for TE. So that is how we determine the exit temperature. Okay. Also, once we know what our exit specific volume is, so once we know the mu sub E, exit specific volume, we can then solve for our exit velocity. Using our mass flow rate equation, which of course is the following: m dot E is equal to our exit area times our exit velocity divided by our exit specific volume. And then of course, if we now look at these parameters, we know that from our conservation of mass, m dot I is equal to m dot E, and AE, the exit area, is given. Okay? Okay, so we can now let the rubber hit the road, so to speak, and start to analyze this further. Okay, so the first thing that we need to do is we need to, if we look back in our solution method here, we need to, we know Pi, that's given to us in the problem statement, but we have to look up Vi, the inlet specific volume, using both Ti and Pi. Okay, so to do that, we'll go to table A6. Okay. In fact, actually, we can even back up a minute. We can say, okay, well, you know, how do I determine my state I property, right? What is Vi? So we know TI and PI, how do I use this to find VI? Okay, so we can do this pretty handedly, pretty straightforwardly. Okay, and what I recommend is relying on the temperature, pressure, or excuse me, the temperature specific volume diagrams that we've talked about. So if I just go ahead and I replicate that here, and so let's suppose that I'll make it nice and big so that we can see it. Okay, so let's suppose that this is temperature and this is specific volume. We go ahead and draw our saturation dome on here. Looks something like that, basically. And let's suppose that we just sort of say that this is TI here. So everywhere along that dashed line, we have TI. Okay, and we know that TI is equal to 450 degrees C. And so, in fact, I probably already, in fact, I did. I already made a mistake in drawing this diagram because 450 degrees C is above the critical point. So let me fix that so that we can do this correctly. So in fact, I'll just go ahead and make my saturation dome quite a bit smaller here. Just erase much of this here. Okay, so I'll just go ahead and make a smaller saturation dome. Okay, and because I know that my critical point temperature, the temperature at this point here is 373.95 degrees Celsius, based on where the critical point data is in my table. So I'm up here at 450 degrees. My temperature scale. This is T. So state I is going to be somewhere along this dashed line here. Okay. And in addition to knowing that I'm at 450 degrees C, I also know that I'm at a pressure of 6,000 kPa. Now 6,000 kPa is well below the critical point pressure, which is 22,000 kPa. And so I can say that perhaps this line through here is my 6,000 kPa line. So this is a pressure equal to 6,000 kPa. Okay. And so, of course, what you see is that where these two lines intersect, where temperature of 450 degrees C intersects with a pressure of 6,000 kPa, that is my state I. Okay? And so I'm certainly in the superheated vapor region, so state I is the superheated vapor. Which then means that I'm going to look in table A6 for my data. Okay? Okay, so let's go to table A6. And when we go to table A6, what we want to do is we'll first find, because remember that table A6 is sorted by subpressures, so I want to find the pressure subtable where pressure is equal to 6,000 kPa. That's the first thing that I do. Then I find where my temperature is equal to 450 degrees C, and where I have that combination of 6,000 kPa and 450 degrees C, I can look in the specific volume column of data and find that my specific volume is equal to 0.05217 cubic meters per kilogram. Okay, so I can show you, if I can manage to get my iPad to go to the computer screen well here, I can show you in table A6 where that table entry occurs. So, photography, camera, and I think I can just do it right like so. So if I do this such that the iPad doesn't cover up the light, I come over here, and so you can see first of all that I'm in table A6, superheated water table, and there you see the pressure subtable for 4,000 kPa, 4 megapascals. Okay, so I come down until I find the pressure subtable of 6,000 kPa, which is right here, and then I find the 450 degrees C temperature. Okay, so let me show that for you. So I put the piece of paper there now where you can see where the 450 degrees C occurs, and I've got a shadow here from the light. Okay, there we go. And you can see now the 6,000 kPa, 450 degrees C, and the table entry there of 0.05217 cubic meters per kilogram. Okay, so that's where we find the data in the table. So we now know state I, at least we know the specific volume at state I. Okay, and recalling that the pressure, volume follow that polytropic expression, that polytropic behavior, we can then determine our state E, our second independent property at state E. So to do that, we can go to a new page here. And so recall that our inlet pressure times our inlet specific volume raised to 1.2 is equal to our exit pressure times our exit specific volume raised to 1.2. We know PI, we now know VI, we know PE, so we can rewrite this equation such that we solve directly for our exit specific volume. So VE is equal to pressure, inlet pressure, PI, times inlet specific volume raised to the 1.2, all divided by exit pressure, and that whole expression is raised to the root of 1.2, 1 over 1.2. Okay, so we now have this expression, and we can start to plug numbers into the equation. And so our inlet pressure is, of course, 6,000 kPa. And our inlet specific volume is 0.05217. And of course, this gets raised to 1.2. Now let me put the units in there as well. So this is 0.05217 cubic meters per kilogram raised to the 1.2. And this is all divided by our exit pressure, which is 100 kPa. And then this whole expression is raised to the root of 1.2. So 1 over 1.2. Okay, so we can plug that into our calculators, and when we do that, we'll get a number that's equal to 1.58 cubic meters per kilogram. Okay. So that gives us now our exit-specific volume. Now we have two independent properties at the exit state. So we have our exit pressure, which is equal to 100 kPa, and our newly calculated exit-specific volume, which is 1.58 cubic meters per kilogram. Okay, and so now we need to use these two pieces of information, the exit pressure and the exit-specific volume, to determine our exit temperature. And again, when we look at those two properties, we won't necessarily know which table to look in. And so to avoid that issue from happening, again, I'm a strong advocate, strong proponent of using pressure volume and temperature volume diagrams. So let's go ahead and draw this now on a pressure volume diagram because we know our pressure and we know our specific volume. So this will be on a PV diagram. And we can go ahead and draw our saturation dome on here. Okay. And we know that our pressure is at 100 kPa, which is of course well below the critical point, so we can draw this down here. So everywhere along that line is 100 kPa. We know that our exit state is going to be somewhere along this line at 100 kPa. Okay, but our specific volume is 1.58. So does that mean that we're somewhere out here as a superheated vapor? Or are we a saturated mixture? Or are we a compressed liquid? Are we somewhere with a very low specific volume? The only way that we can really answer that question is by knowing these 2 points, the saturated liquid specific volume and the saturated vapor specific volume. And of course, we can look those up, right? So our saturated our saturated liquid specific volume, this value right here, our V sub F, okay, and our saturated vapor specific volume, V sub G, we can look those up in our tables, right? So we can look up in table A5, for example, at a pressure of 100 kPa, we have the saturated liquid specific volume at 100 kPa is equal to 0.001043 cubic meter per kilogram. And our saturated vapor specific volume, V sub G, is equal to 1.6941 cubic meters per kilogram. So this value here, the saturated vapor line at 100 kPa, is equal to 1.6941, which is greater than our specific volume at the exit state, which is 1.58. So that means that our exit state is a saturated mixture. We're to the left of the saturated vapor line, but well to the right of the saturated liquid line. So we can go ahead and draw on here our exit state, and we can use our maroon red and say that, you know, perhaps this here is our exit state, V sub E. Okay. Okay, so, well, now, since we've confirmed that our exit state is a saturated mixture, right? So using these two pieces of information, what we do is we confirm that V sub F is less than our exit specific volume, which is less than V sub G. So that means that state E is a saturated mixture. Okay. Now, because state E is a saturated mixture, that means that our exit temperature is going to be the saturation temperature at a pressure of 100 kPa. So TE will equal Tsat, the saturation temperature, at 100 kPa. And of course, we can get that from table A5 as well, from the saturation table data. And that saturation temperature at a pressure of 100 kPa is equal to 99.61 degrees Celsius. And again, I can try and show you that using the camera option and hopefully not creating a shadow here. See if I can create some additional lighting. Maybe that'll help. Oh yeah, that helps. Okay, so once again, we're now in table A5, so we can see that at the top here. We're looking at table A5, and when we scroll down with table A5, if you look at the piece of paper there, at 100 kPa, notice that the data to the right of the 100 kPa is the saturation temperature. That's the temperature of the water when it's at a pressure of 100 kPa, saturated at a pressure of 100 kPa. And so, of course, that's equal to 99.61 degrees C, which is what we've determined our exit temperature to be. Okay, very good. So that answers that part of the question. So then the final question that we have to answer is, what is the exit velocity? Well, we already know what our exit specific volume is, so we can just use our mass flow rate equation to determine what our exit velocity is. So we have that our exit velocity. If I just manipulate my mass flow rate equation, I can say that my exit velocity is equal to the exit flow rate, mass flow rate, times the exit specific volume, V sub E, all divided by the exit area, A sub E. And I know all these values. We already established that the mass flow out is equal to the mass flow in based on steady state conservation of mass. We've just determined what the exit specific volume was, and the exit area was given to us in the problem statement. So our exit mass flow rate, m dot E, is the 15 kilograms per second. The exit specific volume is 1.58 cubic meters per kilogram. And the exit area, A sub E, is 0.22 square meters. So when we plug this into our calculators, we get an exit velocity of 107 meters per second. Pretty fast. I actually came up with this data for this sample problem using actual turbine specification data. So that gives you a realistic sense of what the steam velocity leaving a turbine, what its exit velocity, how fast it is leaving the turbine. course, going into the turbine, it's a much higher velocity, in fact, a velocity that's likely approaching the speed of sound. Okay, well, if you have any questions about this, please send me an email or post a question to the discussion board. Thanks very much for listening, and I'll see you in class.